a current flowing from VDD all the way to ground through Q1, so the device is on. So on Q1 side, we know what is the equation of the current of Q1, which is half K prime W by L V of V squared, and we know that this current is equal, and the current flowing here is equal to 0, so all of IREF is going to flow into Q1, and therefore we end up having that ID1 equals IREF equals to VDD minus this voltage here, which is VGS over R. Okay. Then we talked about transistor Q2, and we said that transistor Q2 shares the same VGS by virtue of connection with Q1, and Q2 will be in saturation. Therefore, when VDS2, okay, is greater than VOV2, which happens to be the same as VOV1, which we will refer to as VOV. Okay, لأنه they share the same VGS. And in this case, if Q2 satisfies based on what circuit is connected to it that VO is greater than VOV, then the current equation for Q2 will be saturation region equation, which is half Kn prime, but this time times the WL2, which is transistor 2 size, and multiplied by VGS minus VTN. And we said last time, if the two devices have the same K prime and the same VT, yani if those two equations really share this variable here, so they share the same K prime and they share the same VT, then those two quantities will be equal, and accordingly we will find that the ratio of ID2 over ID1, okay, the ratio of ID2 over ID1, which is equal to the ratio, so this is equal to the ratio of ID2 over ID1. If we take the ratio of those two quantities here, we will end up with the ratio of IO over I reference equal to the ratio of W by L2 over W by L1. لأنه ID2 is really equal to IO, and ID1 is really equal to IREF. Okay, so whatever I design for to flow in the resistor is going to flow at the output I adjusted by the ratio of the weights of the size of the transistors. Okay, if this is clear and there are no questions, we can move to the next slide. And on the next slide, we say that this is interesting. Now I can adjust the weight of the reference current. Not that because we like things to be complex, but because it is really used on chips everywhere. And the basic concept, and I'll show you a small figure now, is that we can have one I reference, and we will see this later. Okay, one I reference branch of chip, which is expensive to implement, or on the chip, which is expensive to implement. And anytime I want to mirror the current into a certain branch, okay, I need to put a transistor Q2, okay, sharing the same gate to source voltage, and I can mirror the current times the width ratio. Now I'm going to ask you a question now. If we have another connection here going into another transistor Q3, what is the current that is flowing here?
IREF
times the ratio of W by L3 over W by L1, right? Times IREF, right? So practically speaking, if this is too expensive to implement, from now on, as long as I am sharing the same gate voltage, and as long as I am guaranteeing that the VDS3 allows it to be in saturation, I am mirroring the current, and I create as many of these as I want. Okay, thank you. So هلا I'm going to remove this, and I'm going to show you where this is used. So you can see here, for example, in this variable gain design, we have many of these current sources. So anytime you see this in a circuit, it is really generated from such a design, okay? Or from a cascaded design, يعني a single R and many of these branches sent to different sections of the design. So we really use it on chip to implement current biasing. Okay, great. طيب هلا let us now look at the effects of channel length modulation. So as we know, for channel length modulation, let us write the equation. For channel length modulation, the current, instead of being half K prime W by L times V of V squared, we will really multiply it by what?
1 plus VDS over VA.
Right, so we need to multiply 1 plus VDS over VA, right? So if we recall the ratio that we had before, we had I ZO over I reference was equal to ID1 over ID2, ID2 over ID1, and this had the half K prime W by L V of V squared over the same half K prime W by L V of V squared, right? And we canceled those two parts and just kept W by L2 over W by L1, right? So, Hella, if I have the ratio, that this, what am I going to multiply it with? Hella, if I want to add the channel length modulation, the top current is going to be multiplied by 1 plus, this is, what is VDS2?
VGS.
VDS2, هيدا 2. This is 2. VDS2 is?
VD.
VO,
sorry.
VO. So this is VO over VA, okay? And the lower ratio here is really for this current. So the VDS is VGS, right? Because it is the same. So this is 1 plus VGS over VA, right? So in this scenario now, this tells me that what I will end up with is W by L2 over W by L1 times 1 plus VO over VA over 1 plus VGS over VA. When do I get rid of the channel length modulation?
If V0 is equal to VGS.
At the condition when VO equal VGS, otherwise there will be some slight error there, right? That's what we all will know. So therefore, the new equation that we see here now tells me that this is the IO over I reference in the presence of channel length modulation. Now, let us look at transistor Q2, the current characteristics for transistor Q2, يلي هن VO versus IO. It is really VDS2 versus IDS2, right? And by virtue of this portion of the circuit, my VGS is fixed, right? لأن IREF equal ID1 for a fixed R will give me a fixed VGS. So I am governed by having only one curve in the current characteristics at the specific VGS, which is controlled by the left-hand side. Okay, great. When does this circuit enter the saturation? This enters the saturation when VO is equal to what, or when VDS2 equals to what?
Sorry, Doctor, can you repeat the question?
When does the circuit get into saturation Q2, transistor Q2? When VO equals to VGS minus VT. يعني لما بيساوي ال VOV. من هون, from here on, we go into saturation. Here, we don't want it. This is forbidden. Before it, we don't want to operate in it. We will not be doing mirroring, faithful mirroring, right? So the region of operation where this the desired region of operation is really this whole branch. Great. Hello. What is the reference current that I would like for it to operate at? I would like to reflect really IREF. And let us assume for simplicity that W by L2 is equal to W by L1, right? So if they are equal, my ideal current that I am targeting is really IREF, صح? If this ratio is 1, إذا هيدا الراتيو أنا حطيت 1 for simplicity of our discussion, at what voltage VO would I get my ideal response? When VO is equal to what? حسب هاي equation, this equation which we see, according to this equation which we see here, what value of VO, if I guarantee to you that the sizes are equal, will make IO equal perfectly to V reference?
VGS.
VGS. So therefore, at the value of VO equal to VGS, I will get exactly my ideal I reference. Okay, so VO equal VOV, this is the minimum voltage for SAT. Okay, and at VO equal to VGS, I can get my ideal value. Beyond this point or before it, I will get distortion, and this distortion is proportional to what? This distortion is proportional, or the slope of this line here is really 1 over RO2, right? يعني delta I by delta VDS, if you recall from 310, it varies according to the value of VA, and the value of VA really is determines to us the effective intrinsic resistance, output resistance, little RO, and the slope of IDS versus VDS is 1 over RO2. Okay? So, in our assumption here, we are assuming that VA2 equal VA1, also that the devices have the same length and they share the same material, VA prime is the same. Anybody has a question about those 2 points here? Okay, so let us see what the graph on the slide is showing us. Okay, so on this slide here, we can see that the ideal value, if the ratio of the W by L is not 1, is W by L2 over W by L1 times I reference. And this I can achieve it when VO equals to VGS, and that we are assuming here that VA1 is equal to VA2, and we are also have some change with a specific slope, which is 1 over RO2 with respect to the ideal reference. And of course, anything when VO is smaller than VOV is forbidden, because this is linear and I want to operate only in the saturation region. Okay, so I want to operate in the saturation region only. Great. So the output resistance, which we typically study by plugging in Vx and Ix, okay, is RO, can also be defined or derived as delta VO over delta IO. But now we know that delta IO from this circuit in this non-forbidden regular region على delta VO is equal to what over delta VO? 1 على RO2. So therefore, delta V over delta I is RO2, and which is the RO of device Q2. And we already know how to derive it. It is VA over half K prime W by L2 V of V square. And most importantly, it's derived from transistor Q2. Okay? And from this, now we can understand how much we will deviate from the ideal value. So if we tell you that at VGS, if we tell you that RO2 is equal to, let us say 100 kilo ohms, and we tell you that at point VGS, my current was IREF, how much will be the current at VGS plus 1 volt? Will you be able to figure that out?
Yes, نقدر نعمل equation.
Right, so my delta V is really 1 volt, and I will find delta I from it, and then I will add it to I reference, right? So also another thing, for any delta V, which is equal to 1 volt between any 2 points, without knowing the original value of the current, if I have delta V and I have RO, I can find delta I and so on and so forth, okay? So this is just the pure math, okay? Anybody has a question? Okay, great. Now, let's see what the slides are telling us. The ideal value of RO is really the ideal value for RO2, where we want the slope 1 over RO to be 0, meaning we want it to tend to infinity. We want infinite resistance, right? So we don't want to have little RO2 in our circuit, okay? Great. يعني يكون the circuit is ideal for over all the ranges. Let us now look at what the next slide is telling us here. So we have an example, and in this example, they are telling us that we have given VDD, given IREF, okay? We want to design for IO equal 100 microamps. Now, we don't have what the resistance are, so always when they tell us design for, first we need to figure out what the R value is, and then we need, if there is channel length modulation, to force some voltage operation. Now, Q1 and Q2, it is given to me that they are matched. They have the same VT, they have the same VA, and they have the same K prime, and we will write this problem on a separate sheet a little bit, but I'm just reading it for you here. And I'm given what L and W are, and I'm given what VT and K prime are. And they posed for me 3 questions, and those 3 questions are as follows. What is the lowest VO for current source operation? Okay. Given VA prime equal 20 volts per micrometer, find the output resistance of the current source. And then they asked me to find the change in the current when VO changes by 1 volt. So let me share the screen in a second from the iPad, and we will work it out accordingly. Okay. Okay, so let us look at the problem here. Let me see if we can, 1 second, stop sharing. Yeah, let me share again. Okay, so we copied the problem here. Let us look at the current mirror. And they're asking us to first design for this circuit so that it operates at 100 microamps. So what do we know about this circuit? We know that I reference is equal to 100 microamps, right? We know because the current flowing here is equal to 0 that I have here also 100 microamps, right? And we need first to guarantee that this happens. To design for the circuit, we need to solve for R. But to solve for R, let us see what are the equations that we know. We know that this is VDD, and this node is G, and this node is S, okay? We know that I reference is equal to VDD minus VGS over R. Okay, and we know that also I reference is equal to ID1, which is the current flowing in Q1, which is equal to half K prime W by L times VGS minus VT. And since he's already told me there's channel length modulation, So we will say 1 plus, it should be VDS over VA. Let's see what we can plug into those values. I don't know what VGS is to solve for R, so I need first to solve for VGS. I know that this is equal to 100 microamps, and this equation here for ID1 is only dependent on VGS. Let's see. So I can rewrite it as half K prime W by L times VGS minus VT all squared. VDS is equal to VGS for transistor Q1. So this is equal to VGS, and VA is really VA prime times L, okay? And this is equal to 100 microamps. Do I have all the values? Yes.
Yes.
I know what W by L is. I know K prime. I know VT. I know VA prime. I know VL. L of the transistor. So this means that we need to really solve for VGS. And we end up having VGS equal 1.008 volts. Okay, so now that I have VGS, can I find what R is?
Yes.
Yeah, because I know what VGS is, and I know what VDD is, so I can find what R is, and we end up plugging in, and we get that R is equal to 3, which is VDD minus VGS, and sorry, 3 عفوا 3 على I reference, which is 100 microamps. Just be careful with the units when you solve, and this becomes equal to 19.91 kilo ohms. Okay? طيب, great. هلا. Now we decided what R should be, so we have solved for the fact to design for the circuit for this specific I reference. Now, question number 1, which they posed for me, is what is the minimum VO for proper current source operation? So what is the minimum VO?
VGS minus VT.
Minimum
So 1.008
VO,
minus
exactly. We want it to be greater than VOV, which is equal to 1.008 minus VT, which is 0.7. Okay, so we end up getting it to be equal to 0.31 volts. So this is the minimum VO for the operation. Great. The second question, if VA prime is 20 volts per micrometer, what is the output resistance of the current mirror circuit? So we know that the output resistance of the current mirror is equal really to RO2 for this transistor, which is delivering IO, right? So RO2, we know that it is equal to VA, which is, VA prime times L over half K prime W by L times VOV square. I have all of these quantities لأنه هذه هي 20 volt per micrometer. L is given to me as 1 micrometer, right? And I already solved. I have K, I have W by L, which is given here 10 over 1, so this is 10, and VOV square, we just calculated it, and we end up finding that the output resistance RO is 208 kilo ohms. Okay? It's clear, we just applied the equation. The third question that they ask me for is what is the delta IO if delta VO equals to 1 volt? So what is delta IO if delta VO is equal to 1 volt? How do I solve for this?
We know delta VO divided by delta IO is equal to RO2.
صح. So I know that delta VO over delta IO is equal to 208 kilo ohms. And this implies that delta IO is going to be equal to delta VO over 208. And this gives me that delta IO is equal to 4.8 microamps. So So this means the 100 microamps is going to drop by 4.8 microamp if I move away, for example, from VO being exactly at VGS. Yeah, let me also ask you another question. At what voltage VO will the current IO be perfectly equal to 100 microamp? At what voltage VO, if this was the fourth question, at what VO will IO equal perfectly 100 microamps? لما VO equal to what?
When VO is equal to 100 microamps times RO2 نسيت كانت الفاليو.
No, you have to be careful here. Let us go back to this current, it's okay, I can erase this. Let us go back to this equation. احنا شفنا المصفت Q2 حطينا ال VO حطينا ال IO وقلنا انه هيدي ال current characteristics. We said that the minimum VO for operation is at VOV, and then we said that it is going to hit the ideal if this was a slope like this. We said that it is going to hit the ideal. Let me redraw again, sorry. This is the current characteristics, and this is the ideal IREF, right? At what voltage VO do I get the ideal IREF at the output? يعني let us write IO over IREF again. Here W by L equals 1 equals W by L2, right? And VA1 equals VA2. So the ratio is really 1 times 1 plus VO over VA over 1 plus VGS over VA. At what value of VO do I get IO perfectly equal to the 100 microamps?
VGS.
Exactly.
VO equal VGS.
Exactly. So this is at VO equal to VGS. So at VO equal VGS, I will get the exact matching to the ideal voltage. The delta VO over delta IO equal to R tells me the relation at any 2 points. يعني أنا إذا كنت مبلشة من هون ومشيت بدلتا هي 1 volt, what we just found is that the delta for the I تطلع 4.4 micron. Okay, so the delta for the I is 0.4 micron. يعني if I know at VGS equal, at VO equal to VGS, if I know that IO equal 100 microamps, then at VO equal VGS plus 1 volt, IO بتصير 100 microamp plus delta IO, right? So don't get confused by this relation, okay? If it grows by 1 volt, the current will grow by this much. If I know one point, I can know the other. But the point at which it is perfectly equal to I reference is satisfying this relation, is based on this relation, okay? Clear?
Okay, sounds good.
Okay, excellent. طيب. Let us now flip back to the lecture notes. Yeah. Okay. So let me share the screen here again. And okay, sorry, 1 second. Yeah, share screen. Okay, so let us now look at the slides and see how this problem was solved. So you have the current. We found from the current VGS, we found R, we found VO minimum, and then we found the output resistance, and then we find the delta V over delta IO to give me delta I. Okay, great. What we have seen so far is that this circuit is that we have studied is called a current sink. Why do we say a current sink? How is the current I/O flowing? Where is the current I/O flowing? Towards ground or from a supply؟ يعني
from a
هون بعد
supply.
هون بعد حيكون في عنا circuit وهيدا السيركت موصول بال VDD. So the circuit will be above the current source. يعني current source حيكون بينه وبين السيركت حيكون في عندي current source رايح لوين؟ على الجراوند. So it is sinking the current from the supply and the circuit towards the ground. So this is called a current sink. How do we envision a current source to be? It should be directly creating or mirroring a current from the supply, passing it to my circuit. Of course, everything has to flow between VDD and ground. So if we use the NMOS devices to build a current sink, how can I build a current source? Sorry. How can I build a current source?
Maybe we use an PNP MOSFET rather
PMOS.
than
This is NMOS. So instead of the NMOS, we can use exactly PMOS devices, right? Okay. So let us envision how we can draw a PMOS circuit. The PMOS circuit, we should have two transistors, which are PMOS devices, and they are both sharing the same gate G, right? And they are connected to VDD because they need to be connected to VDD to source the current from VDD. Now in the PMOS, we know that the source is always the higher voltage. So we are going to connect the sources to VDD. Now they share the same VSG, right? So VSG is the same for both 1 and 2, right? So this is the Q1 and this is Q2, okay? And here we can have a current source or we can have a resistor going all the way to ground. And this will be I/O. Okay, great. Now, let me ask you a question. Where is the drain of Q1? It's between the resistor. This is the source. Pardon me, sorry. This is the source. So, sorry, but I need to zoom out. Okay, 1 second. Let me see. Okay, so this is the source of the, let me clear. So this is the source, let me draw it again. So we have here the two MOSFETs, okay, and this is the source. We agreed that these are the sources, and this is the shared common gate. Okay, and now we have here, we have a resistor, and this is the drain D. Okay, طيب هلا I will connect the drain to gate, the same as we did here. Okay, so for transistor Q1 that you have here, you will have VSD, right, is equal to what? I don't know, this is double copying now. Is equal to VSG, right? So it's equal to VSG, okay? And will it be in saturation under this condition?
Yes.
It's going to be in saturation. So for 1, so Q1 is in set. Okay, so Q1 is in set. Great. Now the same conditions that govern the NMOS are going to govern the PMOS. What is the criteria? What is the criteria for this? Heidel VO is here. Okay, so what is the criteria for Q2 to be in set?
بدنا VO to be at least greater than or equal to VSG.
Let us start from the rules. We want to have that VSD2 greater than VSG2 minus magnitude of VT, right? So if this quantity is really VOV in absolute value, all of this, what is VSD2? هيدي النوت is VDD. What is VSD? What is VS?
0.
VS, this is VDD, this is PMOS, أنا قلت لكم هي
Right, sorry, yeah, it's VDD, right.
So this is VDD minus VO. Okay, so cycle condition is little bit different. So here we want VO to be less than VDD minus magnitude of VO. Okay, so here we have a slightly different condition because my source is not grounded like in the NMOS, and the condition is on VSD. So always go back to the saturation requirement. This is needed for Q2 to be in sat. Okay, so this is needed for Q2 to be in saturation. Okay, حدا عنده سؤال؟ طيب, great. هلا, from a small signal perspective or from a delta IO over delta VO perspective, what is the effective output resistance of this current source? Am I worrying about IO, which is, what is IO? It is really IQ2, right? So since I am dealing with IQ2 versus the change, VDD is fixed, so the change in VSD is really a change in VO. بيكون الeffective resistance لهيدا السيركت كمان big RO is equal to little RO2. Okay, so big RO for this circuit is equal to little RO2. Okay, anybody has a question about this current source? Great. Okay, so let us now then move to the next set of slides, and let us see what they're telling us here. Yeah. So we learned how to build a current source. We got the answer that the equivalent small signal resistance is really RO2. And now let us look at the circuit here. So this is a simple current source. Okay, so you can see that أهم شيء تنتبهوا إنه S is where you see the arrow, and that S is connected to VDD, and then apply the conditions on VSD versus VSG minus magnitude of VT. Okay, this is what really matters. The rest of it is just pure simple derivation, and the effective small signal equivalent circuit is really RO2. Yeah, when I'm doing small signal analysis, I can remove all of this circuit if I have a circuit connected between this node and this ground. The whole circuit in small signal analysis will see RO2. Okay, so you replace the whole current mirror, all of it, with a simple resistor, okay, اللي هو RO2 between this node and the ground. Okay, that's as simple as it gets in small signal analysis. Okay, great. Let us now look at the same circuit implementation, but this time in
sorry,
the
doctor.
BJT. Yes.
هلا نحن we used a PMOS مع PMOS أو NMOS مع NMOS، بس شو بصير إذا عملنا NMOS مع PMOS؟
Okay, the mirroring requires sharing the same VGS and sharing the same VOV. So for the same current equations to be governed, I have to be using, since it's a mirror, it has to be symmetric, right? Is that true? Where you can use the NMOS, you can use the NMOS to generate this reference current from something else. Okay, but the devices that are mirroring the current, it's a mirror, They have to be similar, so they have to be of the same type. Okay?
Okay, thank you.
Thank you. Okay. طيب great. حلو. Now, just like there is a current mirror in the NMOS devices, there's a current mirror also in the BJT. Now, I have transistor Q1. This is now the emitter. This is the collector. And this is the base. And transistors Q1 and Q2, they share the same base node. Okay. Now, as far as the transistor Q1, I want it to be inactive. And inactive, this means that I want VCE to be greater than 0.3. By virtue of connecting the base to the collector and knowing that there's a current I reference flowing and that the device is on, this means that VBE should be operating around 0.7 volt. But because of this connection here, VBE is equal to VCE, so it is greater than 0.3, so Q1 is guaranteed to be in the active region. اوكي لانه بالاكتف region بيكون عندي الدايود equation بيكون عندي الcurrent is satisfying the property of amplification. Okay, so now for transistor Q2 it will be insat on a simple condition that VO is greater than 0.3. This is very basic, very simple. Okay, now let us also look at a couple of things. The current IC that flows into a transistor is the current that goes directly to the transistor, not the current before this branch. Why? Because here I have IB, okay, and here I have IB2, and now the current that is flowing in this branch is really what? The sum of the two currents. If they were equal, it will be 2IB. If they are not equal, it will be IB1 plus IB2. The same here, this is IC that is flowing into the transistor, but here we have IO equal IC because there is no other current going anywhere else. Okay, so therefore, I reference is really equal to IC plus IB1 plus IB2. Okay, so let us see what they are telling us. And initially we will say that the two transistors are not really similar. And if we say that they are not similar in terms of area, and you don't have to worry much about it, this means that IS1 is different from IS2. And this means that IC1, where the current equation is equal to IS e to the VBE على VT, will be slightly different because of the ratio of IS1 to IS2. Okay, so they're telling me that the base currents, that the current IS are not similar because they are mismatched initially. Now, in the first example, we will assume that beta tends to infinity. If beta tends to infinity, what happens to IB? It's equal to IC over beta. What happens to IB?
Infinity بتصير كمان.
IC over beta 1 over infinity شو بصير؟
Sorry, 0.
0 بصير 0. Okay, so I don't have any branch current in the base to worry about. So in that case, what happens here is that, okay, we start to write the current equations. IREF is VCC minus VBE over R. This is clear because of the short. IC1 equal IS1 e to the VBE over VT, and IC2 equal IS2 e to the VBE over VT. Because IB equals to 0, okay, IC1 is equal to IREF in this case, okay, and therefore the ratio of IREF over IO, okay, the ratio of IREF over IO is really equal to the ratio in this case of IO over IREF, pardon me, let us write it in the proper order. Okay, so the ratio of IO over IREF in this case is equal to IC2 over IC1, which will be end up equal if we take the ratio IS2 over IS1, and we will call this value M. Okay, so it's a ratio that's proportional to the area of the devices. So, okay, so let us see now what the slides tell me. So this means that IO is equal to I reference times M. Great. This is a current source. Okay, I'm reflecting the current under these conditions. Okay, great. And here they are showing us an example how it goes into different circuits on the chip. Now let us assume that M is equal to 1. Okay, and areas are equal, IS2 equals to IS1. And let us now take into consideration the effect of the base current, يعني بتا منها infinity. If M equal to 1, this means that IC2 equals IC1 equals IC, which is IS e to the VBE over VT. So I have IC flowing here and I have IC flowing here. The base current here is IC over beta. The base current here is IC over beta, and the current flowing here is 2IC over beta. Okay, so this means that I reference is equal to IC plus 2IC over beta. Okay, and this means that what is the ratio now of IO over I reference? IO is equal to IC. So we have that IO over I reference equal 1 over 1 plus 2 over beta. Okay, now we all know that if I have 1 over 1 plus 1 over plus some small x, if x is very small, I can approximate it as 1 minus x when x is very small. So therefore, IO over I reference is 1 minus 2 over beta. As a beta is 100, how much is this, for example? 0.98. It's close to 1, but there is an error term. So I have an error term because of the base current. Okay? So I get an error term because of the base current. Great. So the error term is 2 over beta because of the base current. Okay. Now, if we have different BJT areas, يعني is the IC1 not equal to IC2, if M is different from 1, then we get this equation. Okay. And if I have early effect, then the equation becomes a little bit more complex, and I will end up with a value that depends really on VO and VBE and the VAs. Okay, now you will have those equations at your, we are not going to expect that you will derive those equations or memorize them. You will have them when needed. But what really matters is that you are able to derive up till here, and that you understand what it means if IC1 is different from IC2. Anybody has a question about this? Type, okay, great. So know that there is base current and know that there is an error term because of the base current. So this is a simple BJT current mirror as we spoke about it. This is a current sink, not a current source. The small signal equivalent resistance or the output resistance of this circuit is still considered RO2, okay? And how do I build the current source? I build it using PNP devices. Okay, so we build the current source using PNP devices. Anybody has any questions? Okay, we are going to stop here.